Critical thinking, question 17, ranking. And they're asking us to rank these 6 chests, identical chests, based on their final speed when they're acted upon by these 2 forces. So a couple of assumptions here. Well, first of all, it tells you that each chest has only these 2 forces acting on it. So there's no other frictional force or other force we need to worry about. I believe these are overhead diagrams, like from the ceiling looking down on a chest, but even if it wasn't, it doesn't matter. These are the only 2 forces acting on these chests. And they're all the same chest, same mass, and it says the forces will be acting for the same amount of time. So they're going to accelerate if there's a net force, and these all do have a net force. And if you look at Newton's second law, F net equals ma. Well, A is proportional to F over M. A equals F net over M. So these all have the same mass, so the acceleration will be proportional to the net force. The bigger the net force on any given chest, it'll have a bigger acceleration. And if it has a bigger acceleration for the same amount of time, then it will have a bigger final velocity. So that'll be the argument to rank these, is just find the greatest net force. That will correspond to the greatest final speed. Now when you have vectors, 2 vectors in particular, there's a couple ways to add them. There's the way in which you find all the components, which is sometimes the better way. It'll give you a more precise answer. Here we might not need that precise answer. We just have to rank these. I'm going to erase this, I think, and move this down. So the other way to add 2 vectors, you can do it visually. I'm going to kind of do it visually and mathematically at the same, well, you'll see here. You connect them by their tails and draw a scale diagram. For example, what I'm noticing in diagram A is that those 2 vectors are actually at right angles to each other. When you have 2 vectors that are at right angles with each other, combining them pictorially, graphically, and mathematically is pretty easy. B is a little bit more difficult. The diagram I'm going to draw here in a few minutes will be a parallelogram, which is a little bit harder to calculate as far as the size of the resultant of those 2 vectors, but I'll show you a shortcut or sort of a trick on B. C is going to be easy. The net force there is 4. F net is 4 newtons. 4 newtons to the left, because when 2 vectors are lined up like that, you just subtract them. If they're in the same direction, you add them. So I already know the net force there is 4. So if any of the other ones have a bigger than 4 newton net force, they will be ranked higher as far as the final speed, which is, I know, is going to be the case in A and E. By the way, E and A are identical. Their directions are just different. In E, the 2 vectors are at right angles. So I already know before I even start, A and E will have the same answer, the same final speed, because the net force on A and E are both the same. All you need to do is use the Pythagorean theorem in that particular case. For example here, well, I'm going to do A down here. It was 6 newtons and 10 newtons. I don't know if I gave you units, but bottom line is the diagram, if you were to draw a diagram, and I may have you estimate diagrams on the test. I'll give you like options to pick from, or make you calculate this resultant. So that's the resultant there, and to do that, you'd do 6 squared, it would be, well, r squared equals 6 squared plus 10 squared. So r is going to be the square root of 136, because 10 squared is 100, 6 squared 36. R is the square root of 136, which is a little bit bigger than 11, because 11 squared is 121, 12 squared is 144, so r is a little over 11. So I'm going to say it's around 11. I don't have my calculator right now, because we're just going to try to compare these. It's around 11 newtons. Just a little bit more. That's also going to be the case in A, B, C, D, E. This one right here is also F net equals 11-ish. It's going to be the exact same answer as A, is roughly 11 newtons. So that's bigger than 4 newtons, like in part C. So I already know that those two crates are going to have a greater acceleration, greater final speed than crate C. All right, how about in B? Let's go back and look at that again. It has a 10 and a 6, but the 10's at 45 degrees. So we have 10 at 45 degrees, and then the 6. I don't have these quite to scale. Those are newtons. But if you were to draw the diagram that represents the resultant, it's supposed to be a parallelogram, and the resultant will be something like this. I'll call it R. I could call it R sub B. This is R sub A over here, and this is the result for A. This is the result for B. Now, here's the thing. I know that that has to be less than 11. Has to be less than 11. Because when the 10 and the 6 are at right angles, they have the 11, like an A, they're 11. But as the 10 Newton vector starts to angle off to the left, I know for a fact, without calculation here, you could actually do the calculation. You could figure out all the components. You could figure out the x component of 10 to the left, which will be just a little bit bigger than 6. It's around 7 newtons to the left and about 7 newtons up. So those are the two components of 10. You could figure out exactly what R sub B is numerically, like we did some of those in class or in the notes, adding vectors, finding vector components. But I know R sub B is less than 11 newtons. That's R sub B. It has to be less than. As the angle is bigger than 90, and as the angle increases, it's going to get closer and closer to 4 newtons. That's diagram C. So the more that 10 Newton vector angles to the left and starts to point straight left, it will eventually cause a net force of 4 newtons, like in C. But right now it's less than 11. So I know that crate will not accelerate as fast as A and E. All right, then we know what C is already. How about D? Well, D, diagram D, we'll go back, is 6 and 10. Interestingly enough, D, there's the 6, there's the 10. If you investigate this or look at this long enough, actually the shape of that parallelogram is the same as the shape of B. If I draw that parallelogram, in other words, mathematically, if you did all the computations, call this R sub D, the resultant in D, that parallelogram is the same size, same angles. Well, let me double check the angles. Yeah, 45 degrees for the 6 Newton vector. So that's the same as B. It's the same as B. It's got to be less than 11. It's got to be equal to, and it's got to be equal to B. It's less than 11 newtons, and it's the same as B. So those will be tied for the greatest net force, therefore the greatest, or final speed. They'll have the same final speed. Finally, we have one more to figure out. So far, A is the winner. It's got the biggest net force, followed by B and D, sort of tied, and then the last place so far is C. But now we have to look at, A and E are also tied. How about, though, F? Those are both at 60. So the actual angle between those two, the actual angle between these two vectors, I believe it's 60 degrees. Yeah, because you have to have 180 degrees total to form a straight line. So I know in D, I mean it's F. In F, I have 10 and I have 6 newtons. Okay, and this is 60 degrees here. Once again, though, if I draw, and I'm a little off, I'm kind of impinging upon diagram A, but if I draw the vector here, call that R sub F. That's an R sub F. Oh, sorry. R sub F. All right, so once again, mathematically, we could figure out all the components of the 10 and the 6, and it would take a little work there. But that angle is less than 60. So I know for a fact, just visually, because the angle is less than 60, that would be my argument, that R sub F is greater than 11, or greater than the answer in A and E. Because when the angle is less than 90, the two vectors are sort of combining, they're starting to be more and more in the same direction. In fact, if you close that angle up from 60 to 40 to 30 to 20, 10, 9, 8, all the way to 0, then the final result would be 16. When they're both working together in the same direction, you'd have a maximum combined total net force of 16 when they're working together. When they're working against each other, like in C, they'll be 4. So the maximum you can get with these two vectors is 16. The minimum you can get is 4. So the resulting vector has to be somewhere between there. And like in A, it's around 11 point something. In B and D, it was less than 11. But in F, it's more than 11 because the angle's less than 60. So the ranking would be F in first place, followed by A and E tied for second and third place, then B and D tied for fourth and fifth, and then C will be last place. Now we have critical thinking question number 23. We're ranking these by net force of rockets that are moving upward. So all these rockets have turned off their engines. These are the same size and shape rockets, but different masses. So we gotta rank these by net force on each individual. Rank these from greatest to least on the basis of the net force on them after the engines have turned off. A good tweak on this problem would be on a test. I'd say, okay, what if the engines are turned on? I'll go over that in a second here, but let's just look at A for a second. Let's look at rocket A. I will just draw rocket A down here. So this is rocket A. I'm going to do A down here. So we have rocket A. I'm just going to draw it like this. Okay, that's the rocket. Once the engines turn off, all you have, and if we're ignoring air resistance, which I think it says, I'll double check that, we have the force of gravity, F sub G. You can call it W, F sub G. Let me double check, make sure that we're going to ignore. It says ignore any effects of air resistance, because if the rockets are going up, there would also be a downward force of air resistance that would be added to force of gravity as a net force. I'll go over that again in a second. Actually, but once the engines turn off, that is the only force acting on each rocket. It's its force of gravity, its weight. And the force of gravity is W, and it's equal to mg. So the force of gravity on this rocket, or all of them, is mg. I'm going to make it easy on ourselves just for comparisons. Just say F sub g, force of gravity. This is the net force on the rocket. One force. When there's one force, it's easy. It's the mass. It says in case A, it's what? 0.7 kilograms. 700 grams. So it's 0.700 kilograms. And I'm going to call G 10 instead of 9.8. G being the acceleration due to gravity, gravitational field strength on Earth. So the force of gravity, the weight of this rocket right here, is basically 7 newtons roughly. And it's pretty easy to see, and we don't need to go through all the calculations here, that, well, the force of gravity, that is the net force. Net force here, F net here is 7 newtons. F net equals 7 newtons for this rocket. For rocket B, F net equals 6 newtons because it's 0.6 times 10. And then rocket C is 7 newtons. 7 newtons. This one's 4 newtons. And this one's 6 newtons. And this one's 6 newtons. Those are the weights of each rocket. And it's the only force acting. It is the net force. So you can just rank them by those numbers. Now, just for further review, I could say what would this look like? Like if the engines were on, and each rocket had an identical engine, and they were providing, say, 2 newtons of thrust. And then there was, say, let's say 5 newtons of thrust. 5 newtons of thrust for each rocket, and 2 newtons of air resistance. So if you had a situation like that, so 5 newtons of thrust, and what did I say, 2 newtons of air resistance. And I said, say, calculate the acceleration of rocket A. You could do this for any of the rockets, and then rank them by their accelerations. Rank them by their accelerations. Or I could say, what does a free body diagram look like? So this is a bonus question. It's our lucky day, bonus question. So there's my rocket. I already know that this rocket A, I'm going to do rocket A again, the weight, the force of gravity, was 7 newtons. We already calculated that. Air resistance is 2 newtons. Okay, when the rocket's going up, air resistance is down. So, actually, this rocket is going to be slowing down because the thrust is not enough. The thrust, I'm going to make up another number. I'm changing the problem kind of in the middle. I wasn't thinking ahead too much. I'm just making it on the fly. Let's say this is 15 newtons of thrust. So it's still accelerating upwards. If the rocket has less thrust than the weight and the air resistance, it'll still be slowing down. Actually, once it stops, once the thrust stops altogether, the net force, well, it's going to be 9 newtons. It's going to slow down. You know, if your upward force, because thrust is an upward force. Thrust is the upward force. So we'll make that 15. It's supposed to be really long, 15 newtons. All right. So if it's bigger than the other 2 downward forces, it's still accelerating up. But once the fuel burns up, that might lessen from 15 to 14. And once it's all burned up, all the fuel's burned up, and it's no longer an upward force, then the rocket's just going to slow down, come to a stop, and then it'll fall back to Earth. But if you just do F net equals ma, it's a practice problem. F net equals ma. The net force is going to be 15 minus 9. Big up force minus the down force, which is 9. 7 plus 2 is 9. Equals the mass, which is 0.700 times A. So you'll have, what was that, 6 newtons? 6 equals 0.70 A. So then A will be whatever 6 divided by 0.70 is, which will, I don't know, be 0.8 something. Yeah. All right, so that's just an extra bonus problem. Here's an interesting problem, number 24. You have to rank these by the tension in the rope. Tension in a rope is a force. And there's a few head scratchers here as well, maybe. So one thing it doesn't say here, I don't believe, is to ignore air friction. We are going to ignore friction, but I'll make some mention of friction here. For example, in A, if there was friction, if there was a lot of friction, right, that 80 newtons pulling to the right could be offset by 80 newtons. It's unlikely that there's 80 newtons of friction, but there might be 5 newtons of friction or 10 newtons of friction. But let's just say there's no friction. If there's no friction in A, so I'm going to assume no friction. I'll just say it up here. No friction. No friction. Huh, that says no friction. No kidding. All right, well, if there's no friction, then R, which stands for the tightness of that rope, the force in that rope, R here is going to be equal to 80 newtons. I think we got to rank these by rope tension, R. So that's R is 80. And likewise, in B, if there's no friction, R is going to be 45. Because we have an F net of 0. Oops, why did I say 40? Hang on, why is this not erasing? Oh, no. Okay, 45 newtons. So 45 newtons. In C, it's an 80 Newton weight, so it's pulling down. If I were to draw a free body diagram for 8, or for C, there would be an 80 Newton downward force. I drew that, 80 Newtons, that's the weight. 80 Newtons. So this rope right here has to provide 80 Newtons upwards. So R is 80 because it's at rest. When you're at rest, you have an F net of 0. Those are the only two forces acting on that particular weight. That's 80. Now in part D, I'll draw the diagram off to the left here, or off to the right. So this thing weighs 120 Newtons. That's the weight. I'm going to practice my free body diagrams. And there's a 40 Newton upward force. Somebody's pushing on it with 40 Newtons. Well, that's not the scale, but that's 40 Newtons. We have to have an F net of 0. So R must be 80 Newtons. Because 80 plus 40 is 120. So R once again equals 80 Newtons. That'll be tied with C. Let's circle that. These are the important numbers here. This is what we're going to rank by. In E, we're looking for that top rope there. So this rope right here, this rope between the two, I'll point at it. That's not a vector. I'm just pointing at it just to kind of show you where I'm calculating. That rope there will be 60 Newtons. It's holding up the one below it. So that'll be a tightness. So that'll be 60 Newtons. But the top rope is holding up both of the bottom weights. So that top rope R is 100 Newtons. Yeah. And then so by the same reasoning in F, that rope right there is 80 Newtons because it's holding up both weights. The middle rope, this rope right here, once again, is only going to be 40 Newtons. It's only holding up the bottom weight. But this rope right here, R, is 80 Newtons. Now for the tough one. Believe it or not, because it's better if you do this as a demonstration, which I can't do for you right now, but most people are going to think that, well, there's a rope that goes over these two pulleys, and it's hanging with 80 on both sides, 80 Newtons on both sides. So what our gut wants to tell us, well, half the people at least, is that the tightness in that rope, the tension in that rope, the force in that rope, all mean the same thing. The tightness there is 160 Newtons. It's not. Or there's other people who might think, well, because 80 from one way, 80 from another way, so the tightness is 0 Newtons. No, it's got tightness. It's got a tightness. But the tightness, well, it's not 0, because that would be like no tightness, no force. And it's not 160. Believe it or not. The rope there has a tightness, a force of 80 Newtons. R is 80 Newtons there. That's an N there, 80 Newtons. And you can maybe verify this by looking at the free body diagram of each weight. So like this weight right here. What is the free body diagram for that weight? It's at rest. There's a downward force of gravity of 80 Newtons. So there's something holding it up. Now if that upward force was 160, that thing would start flying upwards. But it's not. It's 80 Newtons. That represents the tightness in the rope above that weight. That's why that weight's at rest. It'll stay at rest because F net is 0. Same thing is true for that weight on the left. The 80 Newtons down and 80 Newtons up. But the overall tightness in the rope, one single rope that goes over a pulley, and we're assuming a pulley here that doesn't have any friction in it. So that's a whole other option, but there's no friction in the pulleys here. And it wouldn't change a whole lot if there was friction in the pulleys anyway. But I'll just draw the diagram for the other weight on the left. So 80 Newtons down, free body diagram, and 80 Newtons up, F net of 0. But that one rope there has a tightness of 80 Newtons. And likewise then in H, R is 40 Newtons. 40 Newtons. So sometimes that's kind of hard to believe, but that you could do this experiment where you put two weights like that, across two pulleys, and put a gauge in there, something that can measure tightness, and it'll say 40 Newtons. I guarantee you. Even though it doesn't feel right. Here's another fun one. And we have objects on an incline. This comes down to some of the, I guess, deeper understandings of Newton's 3 laws. In particular, this one's Newton's 3rd law, believe it or not. And I went through some examples in class, but here we have a car pulling a trailer. And different mass trailers, and maybe the car's going different speeds at different times, different accelerations at different times. So, but we don't have to compare, well, what they want you to compare is, in each diagram, the difference between the force that the car exerts on the trailer versus what the trailer exerts on the car. So I'm just going to look at these one at a time. So for example, in diagram A, there's no acceleration there, and it's a light boat, so that it won't be a big force that the car has to exert, but it's going to be a force. I can make up a number. Say this is the trailer. Here's my trailer, and the car has to pull with, say, 1,000 newtons. I'm just making up a number right now, 1,000 newtons. So if that's the force that the car exerts on the trailer, if you remember Newton's third law, if the car exerts a force on the trailer, then the trailer exerts a force on the car. So in that case, if this is the car, that's the car, the force on the car is also 1,000 newtons. Car exerts force on trailer, trailer exerts force on car. They are equal and opposite. That's Newton's third law. So what's the difference between those two? Well, the difference is their direction, but numerically there is no difference. The difference is zero. The difference between the two numerically equals 0. And they're asking us to rank these by the difference between the forces in each scenario. For example, if I go to the second scenario, in the second scenario, the boat is heavier, the trailer is heavier, still a 0 acceleration. But you'll get the idea here. In the second scenario, if this is the trailer, right, it might, but it's the same angled ramp. And it really wouldn't even matter if it's a different angled ramp. But now it might be, say, 2,000 newtons to pull that boat, because that boat's twice as heavy. Well, if the car pulls on a trailer with 2,000 newtons of force, then the trailer pulls back on the car with 2,000 newtons of force. It's a bigger force pair because you have a heavier boat. But what's the difference between those two numbers? Well, the difference between those two numbers is 0. And you can go through all of these. Same thing in C, even though it's accelerating. And to accelerate, you need even bigger forces. Because we're not drawing the total free body force diagram here in these problems. There's other forces acting on the boat. There's the force of gravity straight down. There's the force of friction possibly. And then you could find components like we did in Unit 5. Find components of the weight parallel to the ramp, perpendicular to the ramp, the normal force. We don't need to find all these because this problem is not asking us to draw the full free body diagram. They're just asking us to find the difference between, the force that the car exerts on the trailer and that the trailer exerts on the car. And it's 0. Think about that. That should help you rank that. That's pretty much did it for you. Think about it. Finally, here's the hard one. Well, let's see if it's hard. We got to figure out what the scale says. I'll do A again by itself. So here's A. Here's the person. In the free body force diagram, which is what we want to draw in this case, for the person, we don't want to draw the scale. The scale is what's exerting a force on the person. But there's also the force of gravity. Oh, it tells us the person weighs 600 newtons. So this person weighs 600 newtons. That'll be in every diagram. This one, I'm just doing A first. Do A first. The downward force is 600. And then the scale that he's standing on is going to exert an upward force. How much? That's what we got to figure out. Because whatever the upward force that the scale exerts is what the scale weight reading will be. If you're standing at rest on a scale, it will say 600 newtons, which, by the way, is like it's roughly a 150-pound person. A little bit less than that, maybe. So this person weighs around 150 pounds. So that's what the scale would say if you're at rest, or if you were moving with constant velocity. If you're moving with constant velocity, the scale will say that. But when you're accelerating, the up force, I'll use a different color. If you're accelerating up, which I know we're accelerating up here since the acceleration is 2, the upward force of scale, the upward force of the scale that's applied to his feet is bigger than 600 newtons. Because that's what you do to accelerate up. The velocity doesn't matter. The velocity of 3 meters per second doesn't matter what that is. What matters here is the acceleration. So in this space here, I'm going to cram it in. I'm just going to do F net equals MA for diagram A. F net, this is F net equals MA. Well, F net's big force minus small force. Well, if he's accelerating up, that's the big force. I'm going to call that F, force of scale, F sub S, minus 600 equals his mass. Now, I'm going to I'll go to the top here, or go way over to the right, W equals mg. Your weight, force of gravity, is mass times gravity. We've done enough of these before, but this person weighs 600 newtons, and we're trying to find the mass, and I'm going to take the easy way out. Instead of using 9.8, I'm going to use 10. So the mass is 60 kilograms. 60 kilograms. So I'm going to go back over here to the left, 60 kilograms. And it says the acceleration is 2 in this case. So you're going to get 2 times 60 is 120. So the force of the scale is going to be 120 plus 600. It's going to be 720 newtons in this case. Case A. Case A, the force of the scale is 720 newtons. Now in case B, you're going to do F net equals MA again. F net equals MA. All right, but in this case, all right, it's the same diagram. It's the same diagram as you have over there for A. Okay, far left over here. It's the same diagram, but it's accelerating down now. So the bigger force is the down force. So the force of the scale now is less than 600. Once again, what I like to do is be consistent and take the big force minus the small force. So in this case, it's going to be 600, the bigger force, the down force, minus the force of the scale, equals the mass, which is 60, times the acceleration, which is 2. Now this gives us a different answer if you do the math here. Well, 2 times 60 is 120, but if you move things around algebraically, you can check it out algebraically. I would move the F sub S to the right, and then subtract the 120 from the 600, so you get 480 newtons. So bottom line is, when this guy is accelerating downward, he's going to feel lighter than normal. When you're accelerating upwards, you're going to feel heavier than normal. These forces, these numbers, these weights, these readings that I have circled are how heavy he feels, or the person feels. When you're accelerating up, you feel heavy. When you're accelerating down, it's kind of like you're falling. And the more you accelerate down, the less the lighter you feel. And if you're in free fall, you feel 0. Because you're not floating, you're falling, and there's no upward support force. Now in C, so once again, maybe you've noticed, the velocity doesn't matter in any of these problems so far. And it doesn't actually matter in any of these 6 problems. All that matters is F net equals MA. And it's the same diagram in all 6 cases. That same diagram I have drawn over there to the far left. The only thing that's changing is that blue force of scale. When you're accelerating up, that's a bigger number than 600. When you're accelerating down, like in F, that's the case where you're basically in free fall. And I would round that off. And that last one in F, kind of getting ahead of myself, I would round it off to, because I've already rounded it off to 10, round it off to 10 instead of 9.8. Think about that. But going back to C, the acceleration is 0. F net equals MA. So if you look at in C, F net equals MA, well, F net is the big, well, in this case, the acceleration is 0, so F net is going to be 60 times 0, it's going to be 0. 0 newtons. Because A is 0. That means if you look at the diagram on the far left over there, the force of the scale is 600. They can be moving, the person is moving. The net force is 0. That's a little strange for some of us. That means the force of the scale is 600 newtons. Now, let me say a couple things. It takes a bigger force than that to get the guy going, the person going, like in A. You apply the 720 Newton force for a little while. Then the person accelerates up, you get up to speed, and then you lessen that force to 600. Then you just maintain your speed. If you weren't moving, that won't get you moving. You'll just stay at rest. And that's what the force will be, actually, if you are at rest. But if you're moving with constant velocity, that force, 600, will be equal to the down force of 600. If that force is less than 600, that I just circled there, the force of the scale, like in B, then you're going to be slowing down. Either you're going to be slowing down or you're going to be speeding up downward. You're accelerating down or you're slowing down in the upward direction. Both cases, that's negative acceleration or downward acceleration. So I think I gave you enough information to try to figure out now. You can figure out D, E, and F and then rank these. Interesting elevator problem.